have accomplished a lot in physics. So we say if energy momentum tensor admits a Laurent expansion, which things do, then these are our generators of the conformal symmetry quantum mechanically. And we spend a very long time to figure out the algebra, which is very useful. And today, this cute term that has central charge would actually be useful. So we'll see that quantum mechanically what happens. And what did we do next? What do we do next is, since we have an algebra, why don't we start to build the Hilbert space? Because we can. Because due to state operator correspondence, I can just bring some primary field next to the origin and acting on the vacuum and define a state out of it. And this happens to be the eigenstate of the energy operator that gives us the energy. And the further we discovered that the state is annihilated by all the positive modes. Hence, it qualifies it as a highest weight state. And then the next thing to do is realize, so these guys are basically the raising operator. And if I look at what the lowering operator does, we realize, first, it's nice that it remains an eigenstate of the energy, and it picks up the energy of n. And from this, we conclude, since we have something we can diagonalize, something we can raise the operator, lower the operator, hence we must be able to build the entire representation facing the highest weight formalism. And I can just say there is a bunch of these lowering operator acting on this one. And this is one of the descendants. And all the descendants you can put it in this way. Okay, then today we're going to give a name called chi, because it's too long. Sometimes I will write it's given by a collection of these ni's and the conformal weight. So that's how we label a descendant, is which primary field it comes from and which sets of lowering operator we use. Okay, so that's the Hilbert space. Then we say, well, we have this state operator correspondence. We can go back and forth. Now we have the state. Let's go to find our descendant, which is defined to be the part we throw away from the T phi OPE. And the reason we do this is because the first two terms make sense. The first term, remember, it gave us the level 0 descendant, which is the parent itself, which is the primary field, and then the level 1 descendant, which is the derivative of this guy. And for all the rest, well, it's defined this way. You have to do this OPE to find out. Okay. And the last thing we say, or last thing, which is very important for today's lecture, and remember there's some bunch of counter integral about a word identity, but eventually what we managed to show at the end of the last lecture is suppose I have a descendant. Then we can show that there is some not so pretty looking differential operator, but it's acting just the primaries. So we say, well, correlation functions with descendant doesn't matter. As long as we have all the correlation functions of the primaries, you just find the corresponding differential operator act on it. Okay, so this is where we stand yesterday. Okay? So let's start today's lecture, which is titled How to Build Your Own Unitary Solvable equals to CFT. Okay. So this is what we want to do. Well, unitary it's nice. It gives you more constraints. We want to find the first 2D CFT we can solve that is non-trivial. So, and the unitarity for the people who study particle physics and etc. is something we do require. Okay, and let's first talk about what is unitarity. It really just means, let me take a state. Any state. We demand the norm is bigger or equals to 0. So if I take a state, take the conjugate complex Hermitian conjugate state, I want the inner product to be bigger or equal to 0. Some nice requirement. That's all I meant by unitary. Okay, so of course, that means if we start with a primary, our first demand is all our primaries had better be, normalized this way. Have a positive norm. And then you wonder what other constraints you get. So let's see, level 1. This guy. And then you want to figure out the inner product of this guy and the other guy. I'll write it once today only. Is that when you congregate it become L1. Okay, so you get this guy and you find the bra. But we have this really cute property says that the Hermitian conjugate of a negative mode is a positive mode. Okay, and this we have done a lot. Back in group theory, we say whenever we find a product, we replace it by the commutator, and we switch the position. Because after we switch, since it's the highest weight, it gets annihilated. And if you read off our algebra over there, this gives me 2L0, which is 2H times something we already demanded to be positive, non-negative. So level 1 gave us a constraint. It says that this conformal weight, if you want it to be unitary, it should be non-negative. Okay. So where should I put a really cute graph that we're going to continue building? So remember we start with a AHC plane. I don't need this page yet. So I'll draw a AHC plane here. So naively you'd think anywhere along this central charge you will find a bunch of primaries, not necessarily finite, and they will form a CFT for us. And we just learned if we really want it to be a unitary theory, H can not be negative. That's our level 1 constraint. Okay, next step, level 2. Okay, level 2 has a state like this guy and something more complicated. I'll just look at this guy. And this guy, again, we do the same trick. We find I guess there is a catch. Well, the catch is h equals 0 normally is the identity, so we don't read. We want to study the non-trivial. Okay. Let's see. So this is the commutator we actually want to use our Virasoro algebra because it satisfies this condition which I didn't write, which is when n plus m equals 0, we have the central charge, otherwise we don't. So this one gives me 4L0, so 2 minus minus 2, 2 plus minus 2. And then there's another term, which is C over 2, like 2 times 3 times 1 divided by 2. So this one gives me 4H0 plus C over 2 times something has already been demanded to be bigger or equal to 0. So now let's actually take the identity, look at the descendant of the identity, and this realize we not only need H to be bigger or equal to 0, we need C to be bigger or equal to 0 too. The central charge can only be positive 2. Well, non-negative. So we happily can kill off this part of the plane. So we're only left with the first quadrant to deal with. Okay? And then, of course, remember the level 2. You could do L minus 2. And you could also do L minus 1 squared. And you wonder, what does that impose on our plane? Well, let's hot on that. Because the idea is, now I can switch the gear to do the solvable part, and I realized that problem was taken care of. It's like one stone for two birds. So in order not to repeat myself, I'll just point it out. The two simplest calculation tells us we already only have a quarter of the space left. And we'll come back to this. So we'll hot on this step 1, and then start to think about what do we mean by solvable? Well, remember what's a CFT? The CFT is equals to a bunch of conformal weight comes with a bunch of structure constant plus some constraints on them, which is given by crossing symmetry, which is normally given by this really cute non-Feynman diagram. Has some summation. Okay. So the idea is if you have a 4-point correlation function, I should be able to fuse my operators in whichever order I want. Okay. And then we also hear about it that crossing symmetry from the 4-point function is enough. Anything beyond that don't really give you new stuff. So I would say I claim for some, if I can find the correlation function of a 4-point correlation functions, if I can find all possible 4-point correlation functions, then I claim I solve the problem. Because that will impose all the constraints, and then will give us a bunch H and Cij that will give us a CFT. So that's my definition of solvable. So now let's come back to the last point of yesterday's lecture. So basically now we pull out the genie bottle. and make a wish. Says, what if the left-hand side of that thing equals 0? It says the correlation function of a descendant operator is a differential operator acting on the correlation function. Now I make a wish. What if left-hand side is 0? Then I got a differential equation of the 4-point correlation function. Then that's something I know how to solve, or at least Mathematica knows how to solve. So let's make a wish. Well, as if we live in 2D CFT, whenever you make a wish, like, what if energy momentum tensor is just Karolov, it's only depend on Z? Sometimes they become true. So the wishful thinking is that if I take this chi thing, this chi guy, and find the 4-point correlation function happen to vanish, then we'll be able to say we found a solvable CFT. This is pretty big wishful thinking, and it's actually true. It says, the Gini tells us if chi happen to be also a highest weight state, then your wish is granted. So what do you mean? Well, what I meant is yesterday we built the Hilbert space, but I hide a fun fact. We built a representation of the Virasoro's algebra, but it might not be irreducible. It's actually, we're looking for the irreducible representation. We're trying to say that representation is nice, but except it has infinite number of things. And today what we're going to do is to find this hidden highest weight state and to remove them from the spectrum. And what we're left with would be the real, like the irreducible representation we're after. Okay, well, this is the claim. Let's first say why, if this claim is true, then our wish is granted. Then we'll say, okay, now let's just hunt for this chi. Okay? So what do we mean by a state is the highest weight state? That really just means the definition of highest weight state is this guy. So it says, suppose it's annihilated by all the Rising operator. Then by definition, it is at the highest weight because you can't reason at it anymore. So this line translates to this guy. So suppose this thing is true. Why would the things work out nicely? Okay, let's first make an observation. Is that suppose I take two of these states labeled by the series number of Ni and then the H, and then another series called Ni prime, and some other H prime, and I want to find what's the inner product. So first of all, it's a 2-point correlation function. So it tells us we should have the conformal weight to be the same. And second of all, since they are energy eigenstates, they should have the same energy to have some overlap. Because energy is the thing we diagonalize. If you belong to different energy, your inner product is guaranteed to be 0. So this is the observation, is we have many, many states. But the inner product is only non-zero for special circumstances. Okay? So this is always true. So which means if I found this guy, it's definitely not overlapping with anybody else unless they're in the same lab. right? If they're not in the same level, not the same energy, we don't worry about it. So the only thing we worry about is what if there's a p prime that they share at the same level. If they are at the same level, which let's say start assuming our primary field is not this hidden one. That's the real highest weight. And so we would know it's definitely not level 0, so it's at a level, some level, but as long as it's some level, it can be written as this is a series of stuff acting on this, right? So this operator first acting to the left to produce a state in the same level as the guy we seek after. And then now I wonder what's the inner product. But since this guy is acting on the left, so if now I want these guys to on the right, you take all this permission conjugate, I get a bunch of raising operator acting on this guy. Right? And then, but we already say that this guy is a highest weight, which by definition is annihilated by all this raising operator. So this is 0. So if a descendant happen to be a highest weight state, then we can prove this guy is basically orthogonal to everybody. The ones not in their level, and of course, special case, it's orthogonal to itself, and hence this guy has norm 0, which gave itself a name called the null state, which makes sense. It has 0 norm. Not only it has 0 norm, you take this guy and do inner product with any state, it will be 0. And then you're like, what's the point of this guy? Exactly. So we shouldn't include this guy in our Hilbert space. We just should just throw it away. For example, if again I'm curious about this guy, the correlation about this guy with some other primary field. First, we can use OPE to fuse them. Fuse all these operators except this guy into one operator. It's an infinite number of them, but I don't care. Because no matter what comes out of the OPE of fusion of all these guys will give me 0. Because this guy is a null state. So the claim is true. If we happen this kind of null states exist, indeed our wish is granted, and we will be able to find differential equation of the correlation function, and we will be able to find a solvable CFT. And then, of course, the logical next step will be find null states. All right. So it's again, right, level 1. So level 1. Level 1, there is one guy. So now let's make a wishful thinking says, can this guy be a null state? So null state means it's a highest weight state. It will impose that if L1, for example, acting that state to be 0. Is it 0? It's the same trick. I switch them. And the commutator is all I have left, because as soon as I have a raising operator acting on our starting parent state, it will disappear. And this gives me 2L0 acting on H, which gives me 2H acting on 0. If I want this to be a null state, I get to the identity. Okay, but I say, identity, this operator is trivial, so I'm not interested. Let's quickly move to level 2. So level 2, we have 2 states. There's this guy, and there is the other guy. And of course, the proposal is maybe individually they are not null state, but I might be able to find a linear combination that it's null. Let's see how is this going to be done. Again, let's impose our condition that it is the highest weight. So we use L1 to acting on this guy. Okay. Then the strategy is the same. We replace these guys by their commutator and confidently claim that after it commutes, it will annihilate H, and we don't worry about the other terms. Okay? Now it's the time to play with our algebra. It says 1 minus 2 is 3. 1 plus minus 2 is minus 1. So that's that term. And there's this term. So this term, you must have seen this in quantum mechanics, but it takes literally one line to show that that commutator equals this one. I'm not going to show it. You just bring this L minus 1 here, and there you expand this. It's the same. Okay. And now, you should be doing this L1, L minus 1 commutator very quickly, since we did a lot today, which gives me 2L0. And then this one says, if L0 is acting on H, it reads off the energy, which is H. Let me take 2 out. And then you have L minus 1 left. And this guy says, I'm actually trying to look at the energy of this level 1 state, so it should give me H plus 1, L minus 1. Right? Because this is our J3, or energy. It measures this energy, and this guy measures this energy. So eventually we get 3 plus 2 alpha times 2H plus 1 acting on this guy. Well, so the conclusion is we had a better demand. This coefficient equals 0 if we're interested in null states. So alpha is equals to minus 3, 2 times 2H plus 1. So it says, once we impose condition, L1 acting on this proposed null state, which let's call it a chi, then we find, well, it's not any linear combination. The linear combination is determined by your conformal weight. So again, next one, right? We're supposed to impose a tower of condition, which reads Ln acting that guy equals 0. So one more. So L2 act on chi. Okay. I'll do some side calculation over here, which the only thing needs to be done is replace the L1s with L2s. So I'll do my commutator over here. With this guy is, well, this guy we already did it before. It's 4L0 plus C over 2. And this guy, which means this guy, is L minus 1, L2, L minus 1, plus L1, L2, minus 1, L minus 1. It's just this line, and then replacing L1 by L2. But this guy disappears, because this will give me an L1. Eventually, I always acted on H, so I don't have to worry about this guy. And this guy gives me 2 plus minus 2 minus minus 3. And then 2 plus minus 1 is L1, and there is L minus 1 there. So all this side calculation is understand as eventually it's acting on H. So then this one says I only need the commutator because the other one will annihilate the H. So this commutator we did a bunch of times. This gave me 2L0, so this term gave me 6L. So this is just like scratch paper. And now I can happily write down what's the condition of L2. Acting on chi gave me, first term gave me this guy, which is 4H plus C over 2. And second term gave me this, which is 6 alpha H acting on H. So the second condition gives me, again, this coefficient should be 0. And you can solve C. I decided to not do this algebra because this is really elementary. So say, after you solve this guy, plug the alpha condition in, it should look like 2H times 5 minus 8H divided by 2H plus 1. It is really just plugging alpha in this and solve for C. And you can be somewhat enthusiastic and realize, oh, this is a quadratic equation in H, so I can write down the solution of H2, which is something like this. Okay, I will not bore you with quadratic formula application. So that's basically say H is a function of C and its two lines. So let me first put our two lines on this diagram we're building, and we'll continue. So that you can check, if you look at that formula C in terms of H, you will realize when H is 0, you get a point at H equals 0, C equals 0, so there's definitely a point here. And then there's another point at 5/8. It's the other, the thing in the parameter is 0, C is also equals 0. So that's the 2 point. And then there's a point at C equals 1. This is 1/4. So this point is over here. Since it's a quadratic formula, I'll use my not so confident skills to link them as lines. So basically what we've seen so far is if we want to find this null state, it imposes a constraint says that we should be sitting on that line. Okay? Everybody following? Yes? Continue? Okay, we did L1, we did L2. And next step is L3? No, it should be Ln, right? Remember, we do for 1, 2, and hopefully everything works. So let's see how this works. All right, it better be work. Now we are already on the line. Suppose L3 impose another constraint, L4 impose another constraint, we'll have nothing left. Right? So our only hope is that after we've done with L1, L2, for n bigger than 2, this is just automatically 0. We should be able to see this is indeed true, because if we look at our calculation, we're always trying to move this operator through this mass to be the end, to do some annihilation. But once you go above level 2, for example, this guy, the commutator is something positive. So that will annihilate to H. And then if you do commutator with -1 twice, you step down twice. But if you start with 3, you are still positive. So you're also annihilate. So that's basically, you can do this calculation ridiculously fast because you realize every single term vanishes. Okay, that's good. That means if we're sitting on this curve, we indeed have a level 2 null state. So then we realized, but this is silly, right? If now I'm proposed, let's find the L3 states, even if I'm very familiar with this crazy algebra, it would probably take us until the end of the class. So let's think about a slightly clever way to do this. Okay, the systematic way would be, let's give some names. We'll call V1 is a vector which is given by one of this guy, and V2 is given by the other guy. And now I propose to find the inner product of all of them. So this is just inner product of between all these guys, and this should be equal to that one. And why do we do this? Because remember, this is a degenerate energy state system. So if I find all the inner products, so basically what I'm doing is called diagonalizing. I have a bunch of states. They have some inner product. And then if I make them into a matrix, I must be able to diagonalize it. And more interestingly, if I just take the determinant of this guy, the only way that I'm able to find a linear combination that has inner product 0 means this determinant must be 0. Right? If a linear product, if post-diagonalization, one of these guys is a null state, that means even if without diagonalizing, the original matrix must also have a determinant equal 0. So this is indeed what we can do. But I'm sure you guys now are bored looking at me doing commutators. So I'm just going to find the result. And it's in the notes somewhere that you can look at this pretty 2x2 matrix. And it's not too bad. You get some functions of H. And one of the entry has C. So you can skip the step finding the alpha, the linear coefficient. Just look at this matrix, find the determinant. You can work it out. And then, because this guy, everybody, after you find the determinant, you can cancel an H. And then it's still quadratic, and then you will find this form. So there's two methods are equivalent, except this one is systematic. You don't have to do things like this. Do it for level 1, level 2, level 3, da-la-da-la-da-la. And now, since things getting systematic, this is a very good thing. Because now we can ask our mathematician friends, or maybe somebody really good at computing, says, why don't you just calculate everything for us? Why not? And this guy is called a KEK. And what he found is called a KEK determinant. So he actually calculated everything. So if you just look at that 2x2 matrix and insert dots everywhere and make it a gigantic matrix, this guy find any level n null state. So I'm not going to draw that matrix. That matrix it's a square matrix with a certain level, has partition function of that n, that number of rows and the columns, and it's a square matrix. And he did it. the result is for any level, if I wonder what's the determinant is, it's given by, it's like not only did he do it, he even say factorize it for you so that you can find the H and C line very quickly. So that's just, there's some constant I didn't bother to write down. And it looks like this. And the one thing I have to emphasize is why there is this exponent. So that's why something is determined to be a null state will come up many times. That's because once chi, we found it to be a null state, all its descendants are also null. That you shouldn't be hard. You just dot product, and if chi's descendant would be L minus something econ chi, and you inner product, but you move that L minus thing onto the other thing, it annihilates. So that leaves as an interesting exercise. So that's why there is an exponent. This exponent match our expectation. Once you find null state, all its descendants are null states. So remember our like really, really high tower of representation. In some special scenario, for example, if we sit on that line, then we will find a level 2 null state. So level 2 is every level will, like it will shrink by a lot. Like it's a whole tower of null states get rid of. So that's what that means. And this HPQC, it's not the most enlightening thing ever. I'll just write it down for completeness, and you can check indeed whatever we found over there is this guy taking P equals 1, Q equals 2, which is a level 2 null state. Okay. So Keck did this, says we can do this a lot more times, and now these lines, we can even label them by this PQ guy. And so for example, the two lines we just draw is 1, 2, and 2, 1. And then there is also, if you do it further in level 3, a line appears here. We can label this guy 1, 3. And if you do it for level 4, there might be other lines. This is just one of the important lines. And if you do level 4, there is a line 2, 2 over here. And if you do it for level 6, there is a line 2, 3 over here. And this is a very important line called C equals 1/2. Okay. So after Keck gives us this result, we can just happily draw all the null state lines, and it says if you want to solve the CFT easily, we should leave on these lines. Now let's come back to unitarity. Remember, we halt the unitarity discussion until this result is handed. So let's think about the unitarity. Unitarity says, I want every single state to be norm non-negative. So this has a much weaker condition, says you'd better have the determinant to be non-negative. Once you have a negative determinant, you're doomed. There's no way you have a unitary theory. It's a much weaker condition, but this condition is very easy to impose once we have the Keck determinant. So for example, at level 2, which we calculated very carefully, unitarity says nothing in this curve is unitary. And then you can imagine if you do it, you draw few lines for the level 3 condition, you can shadow more stuff. You can just keep crossing things out. keep putting so every level you draw a bunch of lines, crossing out the part determined become negative, and keep doing that. So then you was like, your best bet, I'm not saying it's definitely going to work. Your best bet is that if you leave on these intersections, then the chance that you get future excluded by further unitary conditions is lower. Your risk, if we were talking about taking chances, the risk is lower if I'm studying CFT on these intersections. They could well be both unitary and solvable. And even better is that if you keep drawing these lines, you realize if we're sitting on intersections, well, now we definitely reduce our primary field to not continuous of them. Furthermore, you can prove that if you sit in this intersection, it gets discretized. For example, the mathematicians show there's nothing happened before 1/2. The first intersection happens at c equals 1/2. And then the second happens at something like 7/10. Maybe. Let me check. Then the third happens to be, but the point is, both C, I didn't bring that part. Both in the C direction and the H direction, it becomes discretized. So for some special number of C, and there are only finite number of primaries. And they are all sitting on these null state lines. And by our argument, we will have differential equations of the correlation functions, and thus they are solvable. So people have done this. Our friends have done this, and then this is what is named the unitary minimum knot model. You can build whatever models you want. They're just saying if you build these models, because we have null states, we can solve them happily. So these models are given as follows. It turned out to be that a C can only take the following numbers. Well, it's an infinite series, but it's like that. And correspondingly, for each M, you can find out exactly where the primary operator's conformal weight is. Again, labeled by this PQ thing. Not terribly enlightening, but you can see that there is a fun fact. If you make a P goes to M minus P, and the Q goes to M plus 1 minus Q, this is actually the same. So there's a symmetry there. It says if I have a PQ weight, it's equivalent to the M minus P, M plus 1 minus Q weight. And this makes sense because these weights happen at the intersection. So one of the PQ labeled one line, the other guy labeled the other line. And then if, of course, you can check if those lines precisely, definitely not precisely, but intersect on the line of C equals 1/2. And a half is when M is equals 3. Okay, so we accomplished. We did build a bunch unitary solvable CFTs. So what should we do next? We solve them, right? So let's try in the next 5 minutes. No, I'm kidding. Now I'm just going to tell you what's half of the homework is up. So one half of the homework is say, don't make this awesome claim. Says OPE in CFT has radius of convergence all the way until where the other operator is. Like if you have three operator and you OPE this to the radius of convergence of that theory is this distance. And that's what we're going to see in the homework. Which is really nice, because QFT, you don't really have that. You have like epsilon radius of convergence. So that's part of the homework. And the second part of homework will take the first guy, as you see, 3 times 4, and you'll see what's going on. And then you will find, P cubed. You take some P cubed, P multiplied by Q needs to be smaller than equal to 3. So there are not many things you can write down out of this. So you write list all the primaries allowed, and which I can tell you one of them is identity. And then we'll do something with these 3 primaries. Basically, we can write down the 4-point correlation function. Remember, the 4-point correlation function consists of something determinant by the conformal symmetry and some function of cross ratio. But now, because this is a minimal model, we have a null state at level 2, which means we will have a differential equation. So let's solve that differential equation and find what's this function of cross ratio. Sometimes some variation of that is called the conformal block. So you can actually solve it. And then after you solve it, you can impose condition on your structure constants, all those CIJKs. Then now you claim I solved the theory. I know all the H, which is given by that formula. And furthermore, I know all the C's. So the structure constant tells you, so how specifically, basically the structure constant tells you how this 3-point correlation function behaves, but which you can also say it as, so if you have this guy, you can understand this is called a 3-point correlation function. But you can also understand this as the fusion of these 2. You manage to expand this in terms of the primary. It's the same. You OPE this guy, and then you inner product to that guy. So basically what you are going to see is that nice thing happens in minimal model that you're going to solve is that the primary operator, when you fuse together, it's sort of like the Klein-Gordon thing you did in quantum mechanics. It truncates. So remember when we proposed this OP, we said, this thing is going to happen, but who knows what will come out? It could be all possible operators in my theory. But in this guy, you can actually write down how they fuse together, and the only thing that pops out, it's themselves, because it's closed and truncated indeed to this finite number of primaries. So then, you will compare this with something you're probably way familiar to it than me. It's the 2D Ising model. So this CFT we found, remember we have no action. We're just playing with symmetries and trying to write down correlation functions based on symmetry, trying to write down correlation function by solving differential equations. And then you realize after you find this conformal weight, which is known as the critical exponent in the other language, and you start to realize, wait, this is something I'm familiar with. What I just found is the 2D Ising model. So you will also see that it says, cool, I could just be, very decoupled from the real world. And just say, my goal is to find things I can solve and solve it. And then you realize they have real-world applications. Neat, right? So that's what we're going to do in this one. OK, so this is the end of this lectures, which should be the beginning, since if you look at it in that big orange book, This is probably 10% of that book. So continue onwards, you could look at how other minimal models are related to real world, for example. And also, if you are even more enthusiastic, you can try to say, look, now we have a CFT. Remember in QFD2 week 3, we struggled with a bunch of Lie groups. And you can do the same. You can learn how to put CFTs, study CFTs coming with Lie group symmetry. Or sometimes it's a fine Lie group symmetry. And then if you say, hey, our motivation is string theory. And string theory worksheet could be all kinds of different genus. So you can look at what happens if I put a CFT on a torus. So those are possible future learning by yourself enjoyment you can have. But I will end here. And tomorrow we have no lecture. This afternoon we have a Q&A. And on Monday, you guys will switch gear to study anomalies. Okay, so let's go.